All right, so lesson 4 is on 14 basic parent functions and their transformations. Most of these functions you should know already. Some of them you will have never seen. We'll talk about them throughout the year. So the first one is the constant function. So f of x is equal to some number, c. Okay, so if f of x was equal to 2, like the picture, it would just be a horizontal line. That's the same as y equals 2. That's what a constant function looks like. So a constant function like y equals 5 would just be a horizontal line with a y-intercept of 5. Okay, the identity function. This is the line y equals x. So I was tutoring someone the other day and they were like, am I supposed to know what that looks like? I'm like, yes. When you're in pre-calculus, you should know what y equals x looks like because it's y equals 1x plus 0, isn't it? So it starts at 0 and you go up 1, right 1, up 1, right 1. Okay, so the function y equals x is called the identity function. Let's think about why it's called an identity function. Every single point, so if I plug in 10, what do I get for y? 10. Okay, so every point on the line, its output is the same as what its input was. So it's the same, identity. All right, so how about the domains and range on these? So the domain for our constant function, we can put in any value for x, but what about our range? 2 for this one. So for f of x equals c, let's use just general c, it would be whatever number c is, right? So for the range, if we just have a single point, you can just say like y is equal to c, or you could write it as c, like in roster notation. I don't know if you guys remember roster notation, like where you just list out the items. You could just write it in the little braces. It's up to you. So our domain for the next one is negative infinity to infinity, and its range is also negative infinity to infinity. The absolute value function, do we all know what that looks like? So if you plug in like 3, you get 3 out. But if you plug in a negative number like negative 3, you get positive 3 out. So it makes a little V shape. It basically takes the identity function in the second half of this line, flips over the axis, and becomes positive. So we have a V shape. Did we all know it was a V shape? Okay. So its domain, negative infinity to infinity, but what's its range? 0 to infinity. What do I put on the 0? Bracket. Perfect. All right, the greatest integer function you guys learned in Algebra 2. You didn't like it in Algebra 2. We're not going to do much with it in pre-calc, so don't worry. But the greatest integer function is basically like the greatest integer that is less than or equal to the number you're given. So it has a filled-in point on the left, and it's an open circle on the right. You guys kind of need to exaggerate that. So its domain and range are really strange because you can't have any of the halves. Like you can't have 1.5. 1.7, right? Can't have anything between those numbers. So the domain ends up being, well, actually the domain is okay, because I can plug in 1.5 and get a number out. It's the range that's weird. So our domain is actually negative infinity to infinity. We can plug anything into the greatest integer function. So if I was doing like a t-table, I could plug in 2.1 and it rounds it down to 2. I can plug in 2.9, it rounds it down to 2. I can plug in 3 and it goes up to 3. 3.2 goes down to 3. Does that make sense? So how about its range? Its range is all of the, what numbers? Not whole numbers, not real. Real would include all the decimals as well. Integers, yes, it's all the integers. So you could write it as all integers like that. Or you could shortcut it with using the fancy Z. Did you guys ever use the fancy Z in Algebra 2? Z stands for integers. So it's like a Z, but it's called chalk face bold, or chalkboard bold is what the font is called. It's like a math font. So it has an extra line there. Okay, so it says functions whose graphs resemble stair steps are called step functions. The most recognized step function is the greatest integer function. So that was where we had, it's kind of like you got like a bracket with an extra line. It looks like that. This is defined to be the greatest integer that's less than or equal to x, so it rounds down. The quadratic function. We should all know this one. Do you guys all know what y equals x squared looks like? I really hope. Okay, so its domain is negative infinity to infinity. Its range is bracket 0 to infinity. Cubic function, we feel pretty good with that one probably too. So that's going to be negative infinity to infinity, and its range is negative infinity to infinity. Reciprocal function. Okay, this is kind of a cool one, because if I plug in, you know, like 10, I get a tiny number, 1 over 10. But if I plug in a tiny number, like 1 over 10, I get 10 out. So if I plug in something that's less than 1, like look here, less than 1, I shoot up really, really high. So if I plugged in 1 over 100, I was really close to the y-axis. I go really far up to 100, okay? So you get the reciprocal out. So if I plugged in like 3 over 2, I'd get 2/3 out. Okay, so the domain, what do you guys think? What do we skip over? 0. So it's going to be negative infinity to 0, parenthesis, union 0 to infinity. And the range, same thing, negative infinity to 0, union 0 to infinity, because we skip over y equals 0 as well. Yeah?
What functions have asymptotes?
They're called rational functions, the ones that have asymptotes. So if I had like y equals 1 over x plus 3, that is a form of 1 over x. Okay, but it's been shifted in a certain direction. Do you guys remember your shifts? We're going to be talking about them today. So when you have x plus 3, it actually goes backwards. It goes left 3 units. So that would look like negative 3. And then from there, it would just look like 1 over x. Okay, so that's why it's important to know the parent function so you can quickly sketch things. And if you think about some of the rules that we've learned before, though, where's the vertical asymptote? It's when your denominator is equal to 0, right? That's why it's shifting to the left 3. Okay? All right, so the square root function. The square root function starts at 0, 0. That is a filled-in circle there because we can take the square root of 0. So our domain is bracket 0 to infinity, and our range is bracket 0 to infinity as well. Exponential function. You've talked about this before. It's been a little while. So if you think about e to the 0, what is e to the 0? Anything to the 0 power? 1, except for 0 to the 0. So it goes through the point 0, 1. That's the most important point on the exponential function. But it has a horizontal asymptote of y equals 0, because you can't get a negative number out no matter what you're plugging in. So you could do like e to the negative 100, but that's not a negative number. It's just 1 over e to the 100, right? So there's no way to get a negative number out, basically. So its domain is negative infinity to infinity, but its range, you can't get 0 and you can't get negative numbers. So it's parentheses 0 to infinity. Okay, every exponential function is kind of like that. So like a to the x would look like the same shape. But sometimes we have exponential decay, we call it, and it goes backwards. But it still goes through 0, 1. All right, so the natural log function. So every log function also looks like this. So we have f of x equals natural log of x. It goes through the point 1, 0. Yikes. And its domain starts at 0 and goes to infinity. Its range is negative infinity to infinity. These two are inverses. Do you guys remember the word inverses? So what an inverse is if you have some kind of graph, I don't know, its inverse is a reflection over the line y equals x. Okay, those two are inverses of each other. So basically their domain and range switch. All right, and then the sine and cosine functions, you guys don't need to know this right now, but we're going to learn about the shapes of these graphs later in the semester. So you've seen the word sine and you've seen the word cosine, but we've always talked about them in triangles. Okay, well there's graphs associated with them. So sine of x starts at 0, 0, and then it goes up, down, and back up, and it does one full rotation. And then it's called periodic. So periodic means that it repeats. So this is repeating the same like up, down, up. It repeats that throughout the graph. So it keeps going and going and going. Okay, so we use these are called sinusoidal functions. Lovely word, sinusoidal functions for lots of things. So for like currents, temperature during the day, anything where there's like something repeating, like the moon going up, the moon coming down, the moon going up, the moon coming down. All right, and then the cosine, so its domain is negative infinity to infinity, but the highest point that it gets to is 1. So So that's 1 there. And the lowest point it gets to is -1. So its range is bracket -1 to 1. So same for cosine, it just starts at 0, 1. So the highest point it gets to is 1, the lowest point is -1. And its domain and range are the same thing. So 2 more functions. So we also have the cube root function. It kind of looks like x cubed, doesn't it? It's just on its side. It's the inverse of x cubed. Its domain is also -infinity to infinity, and range is -infinity to infinity. So if you think about, oh, I didn't put the function. It's f of x equals the cube root of x. And then a logistic function is the last one. I'm not going to write like a parent function for that one because there's lots of different logistic functions. We'll just do, this is one that has 2 horizontal asymptotes. So its domain and range, its domain is -infinity to infinity. And its range, it kind of depends on what this, we'll call this C up here. It's bracket, well, parentheses 0 to C. So in this case, I drew the one that went up to 1, but it could go up to other numbers. Okay, so a logistic function, we use this a lot in real life. It's for any population. So remember how I was talking about the fruit fly example, right? Every population is like this. It's kind of morbid, but think about it. So our population is growing what looks like exponentially right now. The population of the Earth is growing exponentially. Is it always going to grow exponentially? Are we going to have 10 billion people, 15 billion people, 25 billion people? I don't know. What's going to happen eventually? It has to taper off because we don't have enough resources to support a population that large. So that's why I'm saying it's kind of morbid. So every population is like this. So like the population of like wolves in Yellowstone Park, like there's going to be a point where there's not enough resources for a population to survive. So there's 2 horizontal asymptotes. It's kind of weird. So we'll talk about that in the next chapter, I believe. All right, so it says you've learned about shifts, stretches, compressions, and reflections in Algebra 2. So let's do a quick review. So when I talk about the different parent functions that you're going to need to know what they look like, I think that it's fine that you don't know a logistic. I think you should probably know the cube root function. Other ones that you should probably know, I would probably know like a basic shape for an exponential and a basic shape for a log function. And same for all of these. Like I would know most of these graphs. I think it's okay if you don't know sine, cosine, and the logistic. Oh, you don't have to know the greatest integer either. I'll let you skip that. But all of these graphs, you should have a basic idea of what those look like because it saves you time. Like if you don't have to do a t-table every time you're trying to graph something, it just saves you time. All right, so if you remember when you talked about vertical shifting, basically it's when you tack on like a +5 or a -2 at the very end of the graph. So you could have something that looks like x squared minus 5, it would go down 5, right? Does that make sense? So you take your x squared shape, you just shift it down, so its vertex is at -5. Horizontal shifting, that's when you have something inside parentheses. So if I had like x minus 2 squared, it ends up going the opposite of where you think it goes. So anything affecting the input, the x value, if it looks like -2, you would think it goes to the left 2. It doesn't. This would go to the right 2. Do you guys remember why that is? I don't know. Do you guys remember that at all? We'll do some t-tables and I'll show you, or some graphs and I'll show you. Vertical stretching and shrinking. So this is affecting a y value. It's affecting something vertically. So it does exactly what it says it does. So if you had 1/2 x squared, your y values are halved. So it's a vertical shrink. Or compression is the word I usually use. Horizontal stretching and shrinking, it's affecting the x value. So it does the opposite of what you think it does. It's inside parentheses with the x, so you might see 1/3 x and then squared. That would be a horizontal stretch. Does that make sense? So it does the opposite of what it says. So if it says 1/3, you're multiplying by 3. So let's try some of these. So it says, we know what the graphs of f of x equals x squared and x cubed look like. Sketch the original graph and the transform graph on the same grid. I need to make this a little bigger. Okay, so this first one. So we have f of x equals 1/2 x squared minus 3. So there are two transformations that are happening here. Nothing is inside parentheses with the x, so we're not affecting the x value. We're only affecting the y values, right? So when I see 1/2 x squared, what am I doing? I'm shrinking. In what direction? Vertical or horizontal? Vertical. So I have a vertical compression by 1/2, and then the -3 on the end goes down 3. Perfect. So let's graph the original x squared function. So the original x squared function goes through 0, 0, 1, 1, -1, 1. How about 2? 2 what? Not 2, 2. 2, 4, and -2, 4, because we're plugging into y equals x squared. How about 3? And then it looks like we're going to run off our graph. So we have those 7 points graphed. So it's like that. That's our original y equals x squared. So what we're going to do from those points is we're going to take all of the points and we're going to halve them, meaning having the y value. So instead of being up at 9, I'm now going to be up at 4.5. Instead of being up at 4, I'm now going to be up at 2. Instead of 1, I'm going to be at 1/2. 0 is the same, 1/2, 2, and 4.5. So I shrink it, I smush it down. It appears to have gotten wider, which it kind of does. It gets wider like horizontally, but it's shrunk vertically. Does that make sense? It's like smushing something down, like if I had taffy and I smush it down really far, it gets fatter when I do that, right? Same idea. And then the last thing is it's down 3, so I go down 1, 2, 3 from each of those points. So where was I? I was at 4.5. Well, lovely. 4.5, so I go down 3, so I'm at 1.5. So that is my final answer. So that is f of x in black. So you might want to use colored pencils on your homework if you have something like this. Okay, so you're just doing one thing at a time. So the next one, so we have x cubed. Well, x cubed starts at 0, 0. We have 1, 1, but now we have 2, 8. So 2, 4, 6, 8. And -2, -8. 2, 4, 6, 8. Our graph looks like that. That is the original y equals x cubed. So we're doing a couple different things here. So we're going to go to the what direction? With the x minus 3? No, right, 3. Yep, it's opposite what you think. I'm going to go vertical compression again by 1/2. And then what direction am I moving? Up 1. Okay. So it's kind of annoying. So 0, 0 would go to the right 3. You would divide the y value by 1/2, or you'd multiply by 1/2, which is halving, so divide by 2. So it's still at 0, and then we would go up 1. So that final point would be there. So I'm going to try to do all the steps in one. So this point right here, move to right here. Because we go to the right 3, we take its y value, which was 0, and we have it. So it's still 0, we'll go up 1. So how about this point? So at 1, 1, we go right 3, so we're here. We take its y value when we have it. So what happens when we have it? And then we go up 1. So we're going to be right here. The next one, so this point, we go right 3, 1, 2, 3. We have the y value. It was at 8, so now it's going to be at 4. 1, 2, 3, 4. And then we move up 1, so it's going to be there. Lots of things. So it's going to be out 1, 2, 3, 4, 5. At a height of 5. Get rid of those other points. Do you guys understand what I'm doing? So one thing at a time. All right, so this -1 is going to go to the right 3. 1, 2, 3. We're going to have the y value. Well, the y value is -1, so it's going to go up to -1/2. And then we're going to go up 1. So it's going to go right there. And then you can kind of see the symmetry with the rest of the graph when you have that. Do you guys see it? So your final graph is like this. So this is f of x. Okay, so they're kind of annoying to graph. I don't ask you to graph them a lot of times. Most of the time I just want you to list what the transformations are. All right, so the next little bit, so it says if something has two horizontal transformations, this will be important in pre-calc when we get to sine and cosine. You have to factor in the inside of the parentheses. So we talked about this in Algebra 2. Not all of you totally got it in Algebra 2, so let's try to get it this year. So it says, for example, if you have f of x equals 1/2 x minus 6, it looks like you shift to the right 6, right? Do you guys agree? And it looks like you have a horizontal compression of 1/2. Okay, however, if you check this on your calculator, you'll see that it actually moved to the right 12. So it looks like 6, but it's really 12. So you have to factor the inside. So before you begin, to give 1/2 on the outside, and then x minus 12. Then from there, I usually get rid of this 1/2 by going ahead and squaring it. What do you get when you square 1/2? 1/4. So I would write it as 1/4 x minus 12 squared. So sometimes when you guys say, oh, it's a vertical compression, and I'm like, well, in the original it was actually like a horizontal stretch. Those are actually the same thing. They're just by different numbers. So when you think there's a horizontal stretch of 1/2, it actually turned into a vertical compression of 1/4 for the x squared one. For x cubed, it would be 1/8. So we have to factor that out. So let's look at this first one. So it says, just describe the graph. Describe how the graph of g of x equals 2x minus 4 squared plus 6 has been transformed from its parent function. So we pull the 2 out, and we still have everything squared. So from here, you could say that it's a horizontal compression by 1/2 if you want to. But I think it's a little sloppy with all these parentheses. So what I do is I square the 2 and I square the x minus 2. So what do I get when I square the 2? 4. And then I have x minus 2 squared plus 6. So that's my g of x function. So I would say that it was shifted to the right 2. The 4 is a vertical stretch by 4. And I would say that it moved up 6. Do those three things make sense? You get it? Otherwise, it's just the x squared function. So when we were doing our math aerobics, we said, oh, it went to the right 2. Vertical stretch, so it stretched vertically. It made it skinnier, right? And then it went up 6 from there. So we went like that, up 6. Okay? All right, so what is the new function after f of x equals the square root of x has been horizontally stretched by a factor of 2, shifted right 6, and down 3? So horizontally stretched by a factor of 2. So we definitely have the 2x. Oh, not 2x actually, stretched. It's the opposite, right? It should be 1/2. X, and then I'm going to put minus or plus. So I'm moving to the right 6, minus 6. And then down is just hanging off on the end of the function, so down 3. So I would write this function a little bit cleaner. I would write it as 1/2 x minus 3, and then a minus 3 on the end. Sometimes if you want to end that square root, you can put a little line there if you want to show it ends. All right, does that make sense? Sorry, can you see that? Next to the page. So you guys are craning your necks to see. So just make sure that you show that square root ends before you get that minus 3 on the end. Yeah, Greta?
So, like, why is it horizontally stretched if it's 1/2? Because isn't that x smushed or compressed?
It is if it's on the outside, but not on the inside. So the basic example there that I give is if I have y equals x squared, and I have y equals 1/2 x squared, and you think about their t-tables, we know we have 0, 0, 1, 1, 2, 4, right? -1, -1, and so on. Not -1, -1, -1, +1. Okay, here's the tricky part when you think about 1/2 x. In order to get these same y values out, think about what you have to do to the x value. So if I want to get a 1 out right here, 1 for the y, what do I have to do for the x to get 1 out? I have to double it, right? So it's actually a horizontal stretch. It stretches it. So if I want to get a 4 out, I have to put in an 8. I have to double what we had over here. Okay, so that's why anything that's affecting the input actually kind of does the opposite of what you think it does, because you have to undo the operation to get the same outputs. Does that make sense? It's kind of weird when you talk about it. All right, so reflection across the x-axis. So if you have y equals x squared and you're reflecting over the x-axis, every point that you have, so if I had x comma y, its new point is going to have the same x value, but the opposite y value, right? So if you have f of x, its reflection across the x-axis is going to look like negative f of x. All right, so reflection across the y-axis. So I used a different function for this one. I didn't want to use y equals x squared. Do you guys know why I didn't want to use y equals x squared for this next one? Because it becomes y equals x squared. It's still the same thing. But if I have the square root function and I go across the y-axis, every point that I have, like if I had 1, 1, now I'm going to have negative 1, 1. The x value changes. So it's inside parentheses with the x. Okay, so it says sketch the graph of g of x equals x plus 1 squared minus 3, not by plotting points, but by starting with f of x squared and applying transformations. So let's think about where our points are. So those 5 guiding points I always use are 1, 1, 2, 2, 4, 0, 0, negative 1, 1, negative 2, 4. Do you guys all know those points for x squared? Where are each of those points going to move? They're going to move in what direction? Left, not 4, left 1, and then, okay, and then down. I know, I was like, where'd you get up 4? And down 3, right? So every single point is going to move. So we're going to do left 1, down 3, left 1, down 3, 1, 2, 3, left 1, 1, 2, 3, left 1, down 1, 2, 3. Did I get all of them? Left 1, down 1, 2, 3. That's our new graph. Okay, so as long as you have a couple points to guide you, it's pretty easy to move.